Kia ora, year 13. This video is about loci, and we actually covered these topics in the class, and I'm just doing this video for those people who actually missed the lesson. So loci's definition is a set of points that satisfies given condition and creates a path. Before we go into loci, let's just cover some basic stuff. So the first one is called absolute value, and really we're talking about the meaning of the absolute value. So if you look at here, we have absolute value of 4. What that means is the distance from 0 to 4. We actually covered this before. And the absolute value of -4 is the distance from 0 to -4. And what about this one here? How do we interpret this? This is the distance from 0 to x is 3. And what about the last one that we have here? Now, if you look at it, -2, just think about the translation that we did in the past. When you have -2 on the x-axis, that actually means you're moving to the right by 2 steps. So now we can say that instead of the distance from 0, now we can say this is the distance from 2 to x is 1. Okay, now this time let's have a look at some inequalities. So for example, I have x is greater than 1. And if I want to represent this on the number line, so I draw 1 here. And because this is greater than 1, it doesn't include 1, so I need to use the empty circle. And greater means the right-hand side of 1, so I draw this arrow to show it's going towards the right, and I need to shade every part that is on the right-hand side. Now, if I have x is less or equal to 1, to show it on the number line, again, I label 1. Now this time you have an equal sign, that means that includes 1. So instead of empty circle, I draw a solid point here. And this is less than, so I draw the arrow towards the left-hand side because all the left-hand side part of the 1 is less than 1. Now let's have a look at another example. What if I have x is less than 2 and greater or equal to 0? Now we know that this x is between 0 and 2. It includes 0, so I use the solid dot. It doesn't include 2, so I use the empty circle here. And it's between 0 and 2, so I can draw a curve here saying it's between, and I'm going to shade it this part. Okay, what if now I have x is greater than 2 and x is less than -1? So again, we label -1 and 2 on the number line. Is greater than 2, doesn't include 2, so go towards the right hand side and shade that part, and the less than -1, so circle it and go to the left hand side. So this part is less than -1. Now let's have a look at an example in terms of complex number. Say I have a complex number z, which is x plus I, y. And now I'm going to draw the loci with the condition that real part is equal to 3 and the imaginary part is equal to 4. So if the imaginary part is equal to 4, that actually tells me that this complex number is 3 plus 4i. Now this one is straightforward, so we just draw it on the Argand diagram. So real x is 3 and the imaginary x is 4. Okay, and I can draw a vector to show that this is z. Now let's have a look at another example here. Again, we have a complex number z, x plus equal to z, x plus I, y, and the real part needs to be greater or equal to 3. So the only condition that we need to satisfy is this, as long as the real part is greater than 3. So we have an imaginary axis, real axis here, because we are talking about the real part, so we only need to worry about the real axis. So that's why we have value 3. So we are going to draw the vertical line that actually passes this 3. And since it's an equal sign, so that's why we use this solid line, because we does include 3, this value. And because it says greater than 3, that means it's the right-hand side, so we are going to shade the right-hand side of the straight line. Here's another example. So now we're going to draw the loci that satisfy this condition here, which is imaginary part needs to be less than 2. So now we are going to look at the value of the imaginary part, imaginary axis, which is 2 here. Because it doesn't include 2, so I'm just going to draw the dotted line so that it actually shows doesn't include 2, this value. And because it's less than 2, so it's going to include the whole area that is under this horizontal line. So this is the loci that satisfy this condition. Let's have a look at another example here. So we have this condition here, the real part plus the imaginary part needs to be less or equal to 4. Now what I can do here, I can replace the real part with x and imaginary part with y. So that means x plus y is less or equal to 4. Now when I was looking at this one, that reminds me something, linear equations. So let's treat this as a linear equation. So when x is equal to 0, y is equal to 4. When y is equal to 0, x is equal to 4. So we have two intercepts here. So now I'm going to draw those intercepts. So we have 4 and 4 here. And I connect these two dots. That will give me this straight line. Now, so this straight line represents x plus y equal to 4. However, we also have a less than 4. So what that means is it's going to be covering all the regions that is on the left-hand side of this straight line. And therefore, all this region represents the loci with this condition. Now we're going to have a look at another example here. We have a complex number z, which is x plus iy, and the modulus is equal to 3. But another way to interpret this is we can say that the distance from the origin to z is 3. So we're going to say origin is here, and the distance from here to that origin, to that z is 3. So we can say this can be the point. But I also can say this is another point where it has a distance of 3 as well. And I also can say that this is also another point that has a distance of 3. And this is also another point. And I can just keep tracing it. I can actually have many points on this pathway that has a distance of 3. So if you notice that, now we have a circle. So the loci that satisfy this condition is the circle, the circumference of this circle here, because we know that this distance from origin to all the points on the circumference is 3. Here's the second example. The modulus of this complex number is less than 4. And another way to interpret this is the distance from the origin to this complex number is less than 4. So let's just say from the origin, okay, the distance is 4. We can see here. This is another option. We got lots of options here. But because it's less than 4, not equal to 4, so I'm going to use a dotted line. to create a path. And since the distance is less than 4, so that means every single part that is inside this circle fulfill this condition. So therefore, this is the loci that satisfies this condition here. Let's have a look at example 3 here. So the modulus of z minus 2 is 3. Now, if you remember from the previous example, we say that x minus 2 actually means the distance from 2 to x. So therefore, we can use the same way to interpret this. This is the distance from 2 to z. So now it starts at 2. So we know that 2 is here. And the distance is 3. So 1, 2, 3. So there's 1 point here. 1, 2, 3, another point here, 1, 2, 3, another point here, 1, 2, 3, another point here. So again, it will form the circle, and because it's equal, that means I can use a solid line. And the circumference is actually representing this equation here, which is the modulus of the z minus 2 equal to 3. And we don't need to shade outside or inside because it doesn't mention greater or less than. Let's have a look at another example here, which is z take away this whole thing, 1 plus I. The modulus is equal to 2. Again, I can interpret this. This is the distance from 1 plus 2i to z. And if I plot this 1 plus I on the graph, so real part is 1, imaginary part is 1. So this is where it starts from. From here to that complex number, z is equal to 2. So I say we have distance of 2, so 1 point should be here, another point here. So 1, 2, and 1, 2. And because it's equal to 2, so it actually forms a circle with a solid line. And this circumference is fulfilling this condition that is given. And the loci is the circumference of this circle. Let's have a look at the last example. So I have z plus 1 plus I. The modulus is equal to 3. Now, if I look at it, I want to interpret it so that I can draw the picture nicely. But firstly, I want to have the same format as the previous one here. So here I got a z minus. So I'm changing this to z minus, but I don't want to change the value. So therefore, what I need to have in the bracket is -1, -I. So when I expand it will give me plus 1 plus I, which is equal to 3. So now I can interpret this. This is the distance from -1, -I to z is 3. So the starting point is -1, -I. If I plot that one, so the imaginary part is -1. The real part is -1, and the imaginary part is also -1. And the distance is 3, so I'm just going by 3. 1, 2, 3, and go up 1, 2, 3, 1, 2, 3, and 1, 2, 3. Again, it will form the circle. So I'm going to draw the circle because it's equal. Therefore, the circumference of the circle actually fulfills the condition of this question. So this video will only focus on the visual representation of the loci, but I didn't really go through anything that's algebraic way of actually to show the what loci is. So next video is going to be about how we can actually algebraically show the loci, not just visually or geometrically.